Welcome back to the Learn Along series. We are currently studying NLP with deep learning. Today, I think it's session number 21. I don't know what happened earlier. Looks like my Streamlabs OBS crashed and my internet also got disconnected. Two things at the same time for some reason. So I don't know, but let's basically skip. I was basically trying to show what we did yesterday, but let's just skip through that if uh, because we already lost 15 minutes or so. Uh, and let's jump right into today's tutorials that uh, I was planning to watch. It's just a PyTorch tutorial, but I think it's getting more into RNNs, Lstm, GRUs, etc. So I'll switch the OBS and jump right in.
Hi and welcome to a new PyTorch tutorial. Today I show you how we can implement a recurrent neural net using the built-in Rnn module. In the last tutorial we implemented the Rnn from scratch, and I highly recommend to watch this one first to understand the internal architecture of RNNs. And now today we focus on the implementation with PyTorch's own module, so we don't have to implement everything by ourselves. I will show you how to use the Rnn module, and then at the end I also show you how easily we can switch our Rnn model and use special kinds of RNNs like Lstm and GRU. So let's start, and we are going to use my tutorial about a simple neural net as starting point. So this is tutorial number 13 from my PyTorch beginner course. You can find the link to the video and also to the code on GitHub in the description below. So as I said, this is tutorial number 13, so I already grabbed this code and copied it to my editor. And in this example, we are doing digit classification on the MNIST dataset.
Yeah, so let me also grab the code. I didn't know this was a pre. What page is this? Python Engineer, PyTorch tutorial. So 13. Okay. Is it a good idea to just copy everything and post in a Colab notebook? Let's see. Uh, I'm doing the same notebook. No longer NLM, but okay. Uh, I'll keep on trying to split this into multiple lines, but let's proceed. Or I'll basically take this into my other monitor Oops, I'm the older one. Okay, I think we're good.
Classification is not the typical tutorial to the code on GitHub in the description below. So as I said, this is tutorial number 13, so I already grabbed this code and copied it to my editor. And in this example, we are doing digit classification on the MNIST datasets. And I have to say that image classification is not the typical example for RNNs. But what I want to demonstrate here is how we must treat our input as a sequence and then set up the correct shapes. And it also shows that RNNs can indeed be used to get a high accuracy on this classification task. So last time we learned that the special thing about RNNs is that we work on sequences of vectors here. So we treat our input as a sequence. And there can be different types of RNNs. So in this example, we used this many-to-one architecture. So here we have a sequence as a input and then only one output at the end. And this is our class label in this case. So let's jump to the code. And the first thing we must change is the hyperparameters. So the MNIST dataset consists of images of size 28 by 28 pixels, and last time we squeezed that into one dimension, so our input size was 28 times 28 or 784. And this time, as I said, we treat the image as a sequence. So what we do here now is we treat one image dimension as one sequence and the other image dimension as the input or feature size. So you can see this as that we are looking at one row at a time. So let's comment this out and let's create a new one. So let's say our input size equals, and now as I said, we are looking at one row at a time. So this is 28, and then we also create the sequence length, and this is also 28. And then we change the hidden size to be 128, so you can try out different sizes here. And we add another hyperparameter, and this is the number of layers. And here I set this to 2, so by default it is 1. And this means that we are stacking, in this case, 2 RNNs together, and the second RNN takes the output from the first RNN as an input. So this can further improve our model. And now we want to implement the Rnn class. So let's change the name to Rnn and also in the super method. And then our model down here also now is the Rnn. And now let's delete all of this to start with a new fresh implementation. So now our Rnn still has the input size and the hidden size and the number of classes as parameters. And it also gets the new parameter number of layers. So let's put it in here. So let's say the number of layers here, and then of course we must also pass it to our model when we create it. So this is our hyperparameter. And then what we want to do here first is we simply want to store the number of layers and the hidden size. So let's say self num layers equals num layers. And also self dot hidden size equals hidden size. And then we create the Rnn model and use the built-in PyTorch Rnn module. So you can find this here on the official documentation. So this is the Rnn class that PyTorch provides for us. So we are going to use this. So we create an Rnn and say self Rnn equals, and now this is in the NN module, so nn.rnn. And the Rnn needs the input size, it needs the hidden size, and it needs the number of layers in this order. And then we also use a parameter that is called batch first and set this to true. So this just means that we must have the batch as a first dimension. So our input needs to have the shape batch size, and then the sequence length, and then the input or feature size. So this is the shape that we need to have for our input. And again, you can find this in the documentation. So if you set batch first to true, then here you need this shape. So now what we want to do is, before we pass the images to our model, so last time we reshaped it to be this size. So originally our batch or our images have the size, the batch size, then a 1, and then 28, and then 28 again. So this time we only want to have our batch size and then 28 by 28. So here we reshape it to be this size, and then the 28, the first one is our sequence length, and the second one is our input size. So these are both 28, and the same in our, so this is in our training loop, and then later in our evaluation loop we do the same. So here we also have to reshape it to this size. So now we have our input in the correct shape, and now we need one more layer. So as I said, we are using this many to one architecture. So in the end we have a classification task. So this means that we are using a linear layer and then later the softmax and the cross entropy loss. So let's create one more linear layer. So let's say self.fc for fully connected equals nn.linear. And now here we want to be careful. So for the input size, we use the hidden size, and the output size is the number of classes. And I will explain this later again, but basically, as we can see in this image or also in this image, we only use the last time step of our sequence to do the classification. So we only need the last hidden size as the input size for the linear layer. So this is basically the whole init function. And now, of course, we also need to implement the forward pass. So our Rnn, if we have a look at the documentation, then it needs two inputs, and the first one is the input, and the second one is the initial hidden state. So we need this in the correct shape, and so let's create a tensor with just zeros. So we say h0 equals, and then let's say torch.zeros. And then here the first one is the number of layers. The second one is the batch size. So we get this by saying x.size0. The next dimension is the hidden size. So we say self.hidden size. And then we also want to push it to the device if you're using one. So now this is our initial hidden state, and now we can call our Rnn model. So we say out and then a underscore because we don't need this. And then we say self.rnn, and this gets x and h0. So again, let's have a look at the documentation. So it delivers two outputs. And the first tensor contains the output features or the hidden states from all the time steps. And the other one is just the hidden state for the step n. So we don't need this in this case. So now we have the output, and the output is of size. This is batch size, and then we have the sequence length, and then we have the hidden size. So this is the new shape of our output. And now what we want to do is we want to decode the hidden state only of the last time step. So what we have here, again, let's write this in numbers. So this is n, and then 28, and our hidden size is 128. And now we only want the last time step. So we want to have our out to be in n and then 128. So we get this by saying out equals out, and then we use this slicing here and take all the samples in our batch and then only the last time step. So we can say -1, and then again a colon for all the features in the hidden size. So now we have our out in this size, and now that's why we need the hidden size as the input size for our linear layer. So now we can call that. So now we can say out equals self dot fully connected with our out, and then we return the out. So now this is the whole implementation that we need for our RNN. So everything else stays the same. Turn the out. So now this is the whole implementation that we need for our RNN. So everything else stays the same in our training and evaluation loop. And again, what we have to be careful here is to treat our input as a sequence, and then when we use the built-in RNN, that we use the correct shape, and then we need the initial hidden state also in the correct shape, and then we have to reshape it before we pass it to our fully connected layer. So let's try it out. So let's say python main.py. All right, so now training is done, and as you can see, we get an accuracy of 90.
Okay, I'll try to split the code and then run cell by cell, just to make sure that I don't face any issues anywhere. Let me show you what I'm trying to do. So basically, I've all the dependencies here, then the hyperparameters in the other one. mlist data set in the other one, so I'll run these cell by cell. This is fine. Now what's the issue here? Test loader is not defined. Okay. Batch size. Okay, so this should be somewhere here. After this one, then does this work? Okay. So from the beginning, importing stuff, hyperparameters, mnist, whatever this example is. Okay. CUDA. Unexpected intent. Line 6. Huh. And it takes 4 position arguments if 5 are given. 1, 2, 3, 4. Oh yeah. Did he change? Load on his end for init. He's doing the same thing. Oh no, I didn't add this. Sorry. Number of layers. I basically forgot to add this number of layers. Torch has no attribute zeros. But he's done the same thing, right? Sorry, I was on mute. Sorry. The issue was with the spelling of zeros. Instead of Zeroes, it should be the other. Fantastic. So, 2 epochs, 600 steps each. Did we define this? 2 epochs. That's as 100. Accuracy is 92.87. What did he get? I just realized I did not turn on the sound on. Sorry, I'll repeat.
You can see we get a accuracy of 93%, so our RNN works, and you can see that it can be applied on this classification task. And now at the end, I also want to show you two more Rnn modules, so two special kinds. The first one is the GRU, or Gated Recurrent Unit. And the second one is the LSTM, or Long Short-Term Memory. So both are also very popular RNNs, and I will not explain the theory about them right now. I will just show you how easily we can use them as well with this implementation. So let's use the GRU first. So we can simply say nn.gru, and let's also call this self.gru, and down here self.gru, and everything else stays exactly the same. So it takes the same input parameters. It also needs this hidden state, and then the output is in the same shape. So now let's run this with the GRU and test this. Alright, so now as you can see, the GRU...
What all did he change?
Implementation. So let's use the GRU first. So we can simply say nn.gru, and let's also call this self.gru, and down here self.gru, and everything else stays exactly the same. So it takes the same input parameters. It also needs this hidden state, and then the output is in the same shape. So now let's run this with the GRU and test this. Alright, so now as you can see, the GRU works too, so the accuracy was even higher here. And now as last thing, let's also try the LSTM. So as you might know, for the LSTM we need an initial cell state. So let's use the LSTM. So let's first call this self.lstm, and then here we use n.
I got 98.5% accuracy, by the way. So GRU looks objectively better than vanilla RNN. Let's proceed.
n.lstm.
I'll first just copy this. So I'm making like 3 cell blocks, one with GRU, one with the first one with vanilla Rnn, GRU, then Lstm. Basically just to compare.
The input parameters are still the same. And then here we need an initial tensor for the cell state. So let's call this C0. And this has the same shape. And then here we call the self.lstm, and this needs the hidden state and the cell state as a tuple here. So now this is all we need to apply the LSTM. So let's clear this and run it one more time. Alright, so this one worked too, and you can see the accuracy is 97%. So yeah, so now you know how you can implement a RNN in PyTorch using the built-in Rnn module, and you also know how you can use the GRU and the LSTM. And yeah, I hope you enjoyed this tutorial. If you liked it, then please consider subscribing to the channel and hit the like button, and see you next time. Bye.
So LSTM got 97.86, GRU got 98.5, vanilla Rnn got 92.87. Okay. Now we just try to understand the code even better. We defined the class Nn.module init function, which takes self, input size, hidden size, number of layers. Now this is for Rnn layers, which is 2. Hidden size is just trying to understand what this data is. Let's try to play around with the hyperparameters. So I'm just trying to understand uh, just realize I've been just speaking to myself. So what I'm trying to do is basically read through Rnn's documentation and try to see what are the things that we can play with. Where did we do batch host equals to true? We did that somewhere, right? Oh yeah, here. Nice. Okay. Or I can zoom out a little bit. That's fine. So what if here I do uh, non-linearity? Do I just type ReLU. Does this work? Let's do this. Okay, slightly better. Now just duplicate these and then not run the original one. Okay, now our current accuracy is 92.87. Let's see what happens now. ReLU is not defined. Okay, I think that is why it said like so text.relu. Is that what I have to write? Rnn relu PyTorch. Okay, basically defining the activation. Let's do this as well. The init function self.act. We basically get rid of this line and then dot relu. And then what did we do? right over here, self dot act. The argument input position 1 must be tensor, not tuple. Fair. Okay, now I really got confused. NLP Rnn PyTorch Relu. Basically all the keywords. Yeah, we also didn't experiment with dropout and max length. Still don't see any activation. I think this is a great learn along. I didn't even know PyTorch. I mean, intuitively, I knew. I never really looked, but looking at tutorials from here, but we didn't really find our what we were looking for. Has to see the actualization or activation function. Sorry. Did it already? I defined it, but it didn't. I never called it. If I do out equals to cell dot act x, x is equal to cell. Okay, which is now lower. Interesting. Now, I'm not sure if this is helping or not, but yeah, I'll get rid of these. And instead of two layers, let's just have one layer, right? We already have this fine, so maybe just do this. What? Still so high? Oh, so we're using Atom Optimizer. Okay. I thought we were not optimizing this. see what happens with the GRU and also Lstm subsequently when this is done. I think the accuracy is either the same or it has actually increased. But I think for GRU it has probably decreased because we were north of 98%. LSTM, yeah, okay, it's decreased. Instead of MNIST, my interest was to look at probably some other data about CFAR 10. But do I have to do anything else? Oh, there's the code. Uh, let's see. CFAR 10. I'll just change. I don't think there's anything else required unless it throws an error. It didn't. Fantastic. We have a lot of data now here. But is it complete? Yeah, I mean, what? 98% and it's done. Uh, not complaining. What is this? Okay, I'm not really gonna change anything. Let's just see what happens. Now it makes sense. Shape is invalid for input size of 307. Can we do a shape on these? How do I get a shape of a data set? Maybe I just search for the error. we have this information in here. One, 3, 32, 32. What's the error? Input size 307200. To do whether to do color images. Okay, I see. Similarly, what if we go to MNIST? I mean, it will also show us what's going on there, right? Should have checked MNIST first, but okay, fine, all cool, all good. MNIST. Here, I mean, code. '28 by '28 image. Damn. Which is why our CFAR 32 by 32. Okay, let's do 32 by 32. In where? In here. Input size is to be 32. Sequence is also 32. Right? Would this work? Yeah, let's get to do this. Then here expected input batch size of 300 to match target batch size of 100. Output is of shape 310. This is 100. So the model converts 332 into 310, right? Because that's what we have defined. Input size 32, variance size 500, number of layers is 1, classes is 10. Let's figure out what we can squeeze and unsqueeze. But the output are basically the images. It's a tensor with shape 300, 32, 32. I'm trying to understand what is 300 here. Is anything 300 here? Nothing. How did we get to 300? Saved you guys with my sneezes in time. Out is batch size, sequence length, and hidden size. So these two are 32. I'm assuming batch size is 300. Should say that here, right? Test batch contains 5 training batches, 1 test batch, 10,000, so 300. Okay. Alright, alright. But let's assume. So it's 300 by 32 by 32, right? So that images was this. 332, okay. Got it. Now, getting rid of this, we basically have some N128. Labels is 100. That's what I'm not sure how. Do we do this as 300? Does this change anything? Input batch is 300 to match target batch is 100. Now what's the shape? 310, 100. So nothing changed. So it doesn't matter how many are you sending. Where is labels coming from? Oh, not this code. Yeah. So train loader has labels and has images. Labels is 100, images is 300. Let's not reshape. How about this? Then let's see what happens to images. Input must have 3 dimensions, got 4. So we have to do something here, but it's 100, 3, 32, 32. Oh, images on the first one. I think a little bit of the story makes sense now, because images is 100, 3, 32, 32. So instead of, which gets converted into 310, because outputs is defined as, where is outputs defined as? Oh, I mean outputs is model.images, and model is defined as like this. Input size is 32, reading size 500, and is 1. Okay. So here is where the issue is, right? Input has 3 dimensions, got 4. Now what has 4 dimensions here? We basically killed this switch. Why did it error around here? Or it must have gone back when it's going back to the model's forward pass. But good to know. Inputs must have 3 dimensions. So self number layers, size 0, the hidden layers. Do we need to squeeze something right here? X has to be a three-dimensional, two-dimensional, I think. That is what the issue is. Unless input size, parent size. This is multiplying 100 by 3. I just basically want to prevent this from multiplying. See that? So what is 3, by the way? Where is this 3 coming from? I know 32, 32. Nothing is 3. If I multiply these two, I think we need to understand tensor reshape. Uh, we need better examples than this one. That's what you want to do. Why does it not really give the explanation of what reshape is? That's where getting stuck. Input must have 3 dimensions. Now we just got 2. That's the issue, right? What we do 0, this. Yeah, let's do squeeze 0. I see. So okay, until here we are, I think, fine. Now all we need to do basically images, just create a new, do this for now, sq squeeze. What if I just do this? Squeeze 0. Try to get rid of this one. How about that? How did I make this work? Now I'm more confused. But I think I know the loss is too high. Size of a tensor, 300 must match size of a tensor. Yep, I know how to solve this. I know how to solve this. Oh, this is in the test set. Same thing as here. We have to squeeze this. Oh yeah. Let's redo it, baby. मोइन कोड फिगर आउट हो गया भाई. But the loss is too high. %17% accuracy. Great. But I think I am just satisfied that I've made this work with another data set. Okay, I'll break this one out and see where, I mean, we just had one, you know what, for the time being, let's just try with 2 layers. We should have 1 layer. We can at least have a little bit of an extra fun since this is now working. It's a vanilla RNN, so don't expect too high of results, but let's see how high we climb from 17% accuracy to, I don't know, something. But the loss I see is still too high. I need to increase the epochs probably as well, or maybe even further, more layers. It has decreased. Great. What the heck? Okay, either something is wrong and we don't know, or basically it's not complex enough for the model to get something out of it. I'll just go ambitious and do 4. But I think that's it for today. I'll just let this run in the background and let you guys know what the result comes out to be. But essentially today I think more important point we learned was about getting more hands-on. So I'm happy that I can finally comfortable, I shouldn't say comfortable, but I'm a little more comfortable enough to get into the code and then do some of this tweaking, debugging, understanding what to write where and all of that stuff a little better than yesterday. So I would say a little bit of a daily progress, and I think we're way past time. For some reason the stream crashed earlier in the morning, so sorry about that. I am not streaming on weekends now, so we will meet back on Monday. I'll have to see if we are reviewing lectures, I think 9 through 12, or probably even do a little bit more of coding uh, from an assignment perspective, or even just watching a few more tutorials. I have a lot now lined up for us to watch. But with that, thank you so much for watching, and I'll see you guys on Monday.